Welcome to Chapter 12, everyone. Please take your seats. Up until this point in our horological journey, we have spent all our time deep inside the movement. We have analyzed escapements, gear trains, and striking mechanisms. We've lived in a world of pure, theoretical micromechanics. But today, we cross the boundary from the inside to the outside. We are going to study how we actually protect those delicate mechanics and present them to the human being wearing the watch. Today we begin Chapter 12, L'Habillage de la montre, which we translate broadly as Watch, Case and Habillage. We will cover the components, the environmental protection protocols, and the strict health and safety constraints that govern external watch design. Look at the exploded diagram on your screen. You see a complex stack of glass, metal, and elastomeric seals. The movement is just one small part of this massive architectural assembly. Creating a perfect movement is completely useless if you put it in a poorly engineered case that floods with water the first time the owner washes their hands. Habillage is the engineering of boundaries. It is where the pristine internal world of the caliber meets the hostile external environment of the real world. Let's define exactly what this entails. Let us formally define our subject. What exactly is habillage? In traditional Swiss watchmaking, l'habillage de la montre refers to the complete assembly of parts added to the movement that contribute to its external presentation, its protection, its fixation, and its operation. It is everything that dresses the naked caliber. Why does this matter so immensely? Because the movement is fundamentally fragile. It relies on sub-millimeter pivots and microscopic drops of oil. It must be shielded, yet it must remain fully functional and communicative. Look at the four core functional domains of habillage mapped on the screen. First, protection, HABLFNC01. This is the primary shielding. The case must ensure absolute integrity against dust, moisture, extreme shocks, and magnetism. A compromised seal is a dead watch. Second, wearability, HABLFNC02. The watch must physically adapt to the human body, whether on the wrist, as a pendant, or in a pocket. This dictates lug ergonomics and strap geometry. Third, the interface, HABLFNC03. The habillage converts the mechanical output into readable analog or digital information, and it provides the crowns and pushers required for the user to input adjustments. Finally, aesthetic expression, HABLFNC04. This defines the visual identity, the luxury perception, and the artistic trend of the brand. It is where engineering meets high art. To speak the language of case engineering, we must memorize the anatomy. Please look at the top-to-bottom assembly sequence on the screen, showing the 13 core components of habillage. I will use the French terminology alongside the English, as it is the absolute standard in the Swiss industry. We begin at the top with Component 1, le glace, the crystal, which provides the transparent shield. Next are Component 2, les joints, the critical elastomeric gaskets and seals. Component 3 is la lunette, the bezel, which often secures the crystal. Component 4 is the absolute core chassis, la carrure, or the case middle. Component 5 is la couronne, the winding crown, our primary input device. Component 6 represents les correcteurs, the flush adjusters or pushers. Component 7 is le cadran, the dial, sitting just beneath the crystal. Component 8 are les aiguilles, the hands that indicate the time. Component 9 is le cercle d'emboîtage, the case ring that bridges any dimensional gap between the movement and the case. Component 10 is le fond, the case back sealing the rear. Component 11 are les barrettes, the spring bars. Component 12 is le bracelet, the strap. And finally, Component 13 is le mouvement itself, sitting protected at the very center. You must know these 13 elements intimately. They form the DNA of every watch exterior you will ever engineer or service. Now that we know the parts, we must understand the laws that govern them. Welcome to the regulatory framework of health and environment. As watchmakers, you are not just building machines, you are building devices that sit in direct, continuous contact with human skin for decades. Read the general compliance imperative on the screen. Watches are subject to strict health and environmental protection laws globally. A single violation can result in an entire shipment of watches being legally refused at customs. You cannot ignore this. We must navigate 3 regulatory pillars. Pillar 1, Skin allergens. We are strictly limited in our use of allergenic substances like nickel and chromium in any case or strap materials. We must scientifically prove our leaching rates are below legal thresholds. Pillar 2, radioactive emissions. We must strictly regulate the use of luminescent compounds. The transition from lethal historical materials to safe, modern alternatives is heavily audited by international atomic agencies. Pillar 3, chemical disposal. Under WE and RoHS directives, we are legally mandated to provide safe, end-of-life recycling logistics for toxic battery components. In Europe, these are governed heavily by the REACH regulation. Designing a watch case is as much an exercise in legal compliance as it is in mechanical engineering. Let's drill down into Pillar 1, wearer allergies, specifically regarding metals. Look at the clinical medical photography on the left of the screen. This severe red rash is allergic contact dermatitis. It is the watch industry's worst nightmare. Approximately 10% of the general population is highly allergic to certain metals, most notoriously nickel Ni and chromium Cr. Where do we find these? They are ubiquitous. They are alloying agents in standard stainless steel, they are used in precious metal alloys to alter color, and they are heavily used as galvanic undercoats before gold or rhodium plating. Look at the cross-section diagram showing the ionic leaching mechanism. The metals don't just sit there. When exposed to human sweat, which is acidic, the nickel ions literally sweat out or leach from the alloy, migrating through the plating and penetrating the skin boundary. This is why the EU nickel directive was enacted. Read the warning box at the bottom. It strictly mandates that nickel release must remain below 0.5 micrograms per square centimeter per week for any item in prolonged skin contact. If your bespoke stainless steel case fails this leaching test, it is illegal to sell in Europe. Period. You might think avoiding metal solves the allergy problem. It does not. Let's look at wearer allergies originating from non-metal materials. Look at the component breakdown matrix of the strap assembly on the screen. Even without a single gram of nickel, a watch can trigger severe dermatological reactions. First, consider synthetic materials. The trace compounds, plasticizers, and stabilizers used in resin cases or synthetic rubber straps can be highly allergenic. Second, look at leather straps. The inner tanning layer is often saturated with residual industrial tanning chemicals, chromium salts, and synthetic dyes. Third, look at the structural adhesives. The glues used to bond the layers of a luxury leather strap, or even certain structural adhesives used inside the case architecture, can outgas or leach allergens. The design implication here is massive. As an engineer or product manager, material selection requires rigorous, documented allergen testing. You must demand latex-free, nickel-free, and chemically stable certifications from your suppliers. We rely on strict standards like ISO 24712 to scientifically determine leaching rates before a single watch goes into production. Let us move to Pillar 2, radioactive emissions and the evolution of luminescence. How do we make a watch readable in the dark? Historically, the answer was horrifyingly dangerous. Look at the evolutionary matrix on the screen. In the legacy era of the early to mid-20th century, watchmakers used radium-226Ra and promethium salts. Look at the red warning box. Radium is a severe radiation hazard. It exhibits intense, long-range alpha and beta decay with a half-life of 1,600 years. The dial painters of this era suffered horrific, fatal radiation poisoning. Handling vintage watches today requires strict biological hazard protocols. This led to the transitional era using tritium-3H. Tritium dramatically reduced the hazard. It emits very low-energy beta particles that cannot easily penetrate the watch crystal or human skin, and its half-life is a much shorter 12.3 years. However, it is still a radioactive isotope, meaning its import and export remain heavily regulated and monitored. Today, we operate in the modern standard era. We use completely non-radioactive photoluminescent pigments, such as superluminova. These operate purely on light absorption and emission. There is zero radioactive hazard, zero biological threat, and an unlimited lifespan. This is the only acceptable standard for modern haute horlogerie. While tritium is heavily regulated, we must contextualize the actual risk it poses to the wearer. Let's look at the radiation dose comparison chart on the screen, which tracks the annual radiation dose measured in millisieverts, or MSV. Look at the blue bars. Sitting near a television yields about 0.01 MSV annually. Wearing a tritium luminous watch, specifically one using gaseous tritium light sources on the indices and hands, exposes the wearer to approximately 0.02 MSV per year. To put that 0.02 MSV into perspective, taking a single commercial flight from Zurich to New York exposes you to the exact same 0.02 MSV dose due to high-altitude cosmic rays. Compare this to natural ambient cosmic rays, 0.35 MSV, standard medical sector exposure, 1.20 MSV, or simply breathing the ambient radon gas naturally present in residential homes, which gives you a massive 1.50 MSV annually. The horological takeaway? The actual biological danger of a modern tritium watch is statistically negligible, equivalent to one transatlantic flight. However, the legal and regulatory burden placed upon the manufacturer to track and control these radioactive isotopes remains incredibly severe. Our final environmental pillar addresses the end of the product's life, battery disposal and recycling. Look at the cyclical logistics matrix on the screen. Why do we care about a tiny piece of metal? Look at the hazard profile in red. Watch batteries, specifically button cells, contain severely hazardous environmental toxins. We are talking about highly concentrated mercury, Hg, silver oxide, lithium, and zinc. If these batteries are thrown into household trash, they end up in landfills, where their casings corrode, leaching lethal heavy metals directly into the groundwater table. Because of this catastrophic environmental risk, strict, separate industrial collection is legally mandated. Look at the blue box. The EU Battery Directive strictly forbids standard disposal. It places non-negotiable takeback and specialized recycling obligations squarely on the shoulders of the retailers and manufacturers. Consider the logistical note at the bottom. A single major Swiss quartz watch manufacturer might produce and replace millions of individual battery units annually. Managing the chemical separation, recovery of silver and lithium, and safe destruction of mercury at that industrial scale is a massive, highly regulated logistical operation. We have covered the legal constraints. Now, we must turn to the physical reality. Welcome to the section on external constraints. I call this the environmental crucible. Read the harsh reality in the blue box on the left. Watches are subjected to more severe, continuous chemical and physical stress than almost any other everyday consumer product. A watch sits directly against the sweating human skin, swinging violently through the air, exposed to the sun, rain, and impacts, day after day, year after year. The engineering goals of the habillage are twofold. First, perfectly isolate and protect the delicate movement lubricants from degrading. Second, prevent the rapid structural deterioration of the exterior components themselves. To ensure survival, we test against 4 distinct threat vectors: chemical, thermal, kinematic, shock, and pressure, water. Our baselines for survival are rigidly defined by international authorities. We use ISO, International Organization for Standardization, and NIHS, Normes de l'Industrie Horlogère Suisse, standards. These documents dictate exactly how we abuse the watch in the laboratory to ensure it survives on the wrist. Let's dissect the first threat vector: chemical constraints. We must analyze how atmospheric, liquid, and gaseous contaminants attack the watch. Look at the 3-phase diagram on the screen. Pay attention to the red warning banner. Micro crevices in components act as contaminant traps. The geometry of a watch case is full of tiny gaps where destructive chemicals accumulate and slowly eat away at the metal. Phase 1 is atmospheric contaminants. If you live on the coast, the saline-rich air acts as a corrosive electrolyte. If you live in an urban environment, the air is full of acidic, sulfurized, and chlorinated compounds from exhaust and industry. Phase 2 is liquid phase attacks. The primary vector here is not seawater, it is human sweat. Sweat contains lactic acid and salt. It is highly aggressive. In the lab, we actually test cases by soaking them in synthetic perspiration with a pH of 4 to 5, governed by ISO 105E04. Phase 3 is gaseous ingress. This is an internal threat. Vapors outgassing from cheap adhesives used in strap manufacturing or presentation boxes can penetrate the case seals. These volatile organic compounds can cloud the crystal, dissolve dial varnishes, and chemically alter the movement's microlubricants. If you think stainless steel is immune to these chemical attacks, prepare to be humbled. Look at the forensic grid on the screen. This is visual evidence of chemical corrosion on what we call stainless steel. The myth of stainless is precisely that, a myth. Grade 316L stainless steel provides excellent, but not absolute, protection under aggressive conditions. Look at Exhibit A. This is a solid stainless steel bracelet screw. It has been severely corroded, eaten away simply by prolonged contact with human sweat during a synthetic perspiration test. Exhibit B shows a knurled bracelet pin. The combination of sweat corrosion, abrasive grit, and continuous mechanical bending stress has utterly destroyed the steel matrix. Exhibit C is terrifying. This is a chronograph pusher screw, deeply pitted and rusted by a combination of human sweat and ambient coastal salt air. Exhibit D shows a different chemical reaction, sulfuration. This silver dial has erupted in black spots due to exposure to hydrogen sulfide and sulfur dioxide in standard urban atmosphere. The design directive is clear: you cannot rely on material chemistry alone. Your case architecture must actively minimize physical crevices where these highly corrosive residues can accumulate and fester. We move from chemistry to thermodynamics. Let's look at physical constraints, temperature. What is the thermal operating envelope of a wristwatch? Look at the gradient bar on the screen. The temperature on a human wrist in a climate-controlled room is fairly constant, around 28 degrees Celsius. The human body acts as an excellent thermoregulator. However, when the watch is taken off and stored, it can drop below 0 degrees Celsius. Conversely, look at the visual evidence photo on the bottom left. If a watch is left sitting on a dashboard in direct, glaring sunlight, the surface temperature of the dial and crystal can easily skyrocket to plus 70 degrees Celsius or more. This creates massive engineering mandates. First, for solid materials, the metals, polymers, and sapphire gaskets must tolerate a massive thermal delta, change in temperature, of over 70 degrees Celsius without suffering structural failure, geometric distortion, or loss of sealing integrity. Thermal expansion is a ruthless force. Second, for fluid materials, every single drop of lubricating oil and grease inside the movement must retain its exact, mathematically calculated viscosity. It cannot freeze solid at 0 degrees Celsius, and it cannot separate or evaporate at 70 degrees Celsius. Continuing with physical constraints, let's examine the invisible enemies, solar radiation and magnetic fields. Look at the two diagrams on the screen. On the left, solar radiation, UV. UV photons are highly energetic. They relentlessly bombard the watch, causing photochemical degradation. They will aggressively break down dial varnishes, bleach luminous pigments, and destroy surface coatings. This accelerated photochemical aging causes yellowing, cracking, and delamination. Our countermeasure is utilizing UV-stable synthetic polymers and heavily relying on UV-blocking sapphire crystals to shield the dial. On the right, magnetic fields, or Lu magnetism. This is arguably the most common modern threat. Our homes are filled with electrical equipment, speakers, and magnetic bag closures. What is the impact? If the microscopic steel balance spring inside the movement becomes magnetized, its coils will attract each other. The watch will run violently fast, gaining minutes or hours a day. Our countermeasures? We either encase the movement in a soft iron inner shell acting as a Faraday cage to route magnetic flux lines around the caliper, or we utilize entirely non-magnetic escapement alloys, like silicon. ISO 764 mandates a minimum survival tolerance of 4,800 amperes per meter. Now we face the most violent physical constraint, shock resistance. Let's look at the kinematics of impact. Look at the diagram on the left. Normal brisk wrist movements generate linear accelerations between 10 g and 1000 g. But what happens if you drop a heavy, solid steel watch onto a rigid tile floor? The deceleration is instantaneous. That catastrophic impact generates a localized shockwave of up to 8000 g. Without protection, the brittle jewel bearings holding the balance staff will instantly shatter like glass. How do we test against this? Look at the right side of the screen. We use standardized testing equipment called the pendulum hammer, or mouton pendule. This machine delivers highly controlled, scientifically repeatable impacts directly to the watch chassis to test the efficiency of internal shock absorbers like the Inca block or KIF systems. To earn the designation of a shock-resistant watch under ISO 1413, the watch must survive 3 distinct, brutal impacts at 5000 G, utilizing an 11 millisecond half-sine pulse. If the watch stops, or if its timekeeping rate deviates beyond a few seconds, it fails. We arrive at the final, and most complex environmental constraint, water resistance, or Letenheit. Look at the hydrostatic force diagram on the right of the screen. The fundamental need is absolute: the movement must be completely, hermetically isolated from dust, moisture, and liquid immersion. Water inside a mechanical watch is a death sentence. Let's review the physics of hydrostatic pressure. At the surface, the watch experiences 1 bar of atmospheric pressure. For every 10 meters you dive underwater, you add exactly 1 bar of hydrostatic crushing force. Therefore, at 100 meters depth, the case is being crushed by 11 total bars of pressure. The sapphire crystal is being physically bowed inward, pressing against the seals. The industry recognizes 2 tiers of resistance. Tier 1 is étanchéité normale, or normal resistance. This covers splashes, showers, and brief surface swimming. It is typically rated at 3 atm or 30 meters. This is a static test. Tier 2 is étanchéité pour plongée, or true diving resistance. A watch rated to 100 m under ISO 6425 must actually withstand extreme overpressure tests far beyond 100 m to guarantee absolute safety during dynamic underwater movement. How do we prove a watch is water resistant before selling it? Let's review the verification protocols. Look at the 2 primary testing apparatus types on the screen. Type 1 is the air pressure deformation device. This is a highly precise dry test. The watch is placed in a chamber, and air pressure is dramatically increased. 2 microscopic sensors measure the physical deflection of the watch crystal and case back. If the case is perfectly sealed, the increased air pressure crushes the case inward slightly. If the case has a microscopic leak, the high-pressure air floods inside the watch, equalizing the pressure, and the case does not deform. It is a brilliant, non-destructive test. Type 2 is the liquid column water tank. This is a wet test. The watch is suspended above water in a pressurized air chamber, allowing high-pressure air to enter any leaks. Then, the watch is submerged, and the air pressure is released. If the watch has a leak, the trapped high-pressure air inside the case will violently bubble out through the water, revealing the exact location of the seal failure. Read the red warning box. Water resistance is only guaranteed at the exact moment of testing. Gaskets degrade. Therefore, a documented hydrostatic pressure test is absolutely mandatory after every single case opening. Understanding how seals fail is critical to maintenance. Let's look at water resistance, failure modes, and maintenance. Look at the vulnerable sealing interfaces diagram on the right. A watch case is full of holes. You have the massive opening for the case back, the hole for the crown stem, and the opening for the crystal. Every single one of these is sealed by an elastomeric gasket. How do they fail? Look at the degradation mechanisms. The primary killer is compression set. Over time, the rubber gasket suffers permanent physical deformation. It loses its elastic memory and stops pushing back against the steel walls. Secondary killers include chemical attacks by human sweat, sunscreen, and the very cleaning solvents watchmakers use. Thermal and UV aging also cause the rubber to embrittle and crack. Look at the best practice service flowchart. When you open a case, visual inspection is not enough. You must assume the gaskets are compromised. The professional standard is to systematically replace the caseback gasket and crown O-rings, meticulously reassemble, and perform a mandatory hydrostatic pressure test before returning it to the customer. Hermeticity is a temporary state, maintenance makes it permanent. To synthesize our study of external constraints, let us review the horological verification standards synthesis matrix on the screen. These are the laws of physics codified into international law. Memorize these baselines. ISO 22810 governs general water resistance. It validates watches for splashing and surface swimming, testing up to 200 m. ISO 6425 is the holy grail for divers' watches. It mandates a minimum of 100 m resistance, plus survival under extreme overpressure, thermal shock, and absolute legibility in total darkness. ISO 1413 governs shock resistance, mandating survival against that brutal 5000G, 11 milliseconds half-sine pulse we discussed. ISO 764 governs magnetic resistance, requiring the watch to maintain accuracy after exposure to a 4800 ampere per meter electromagnetic field. ISO 3159 is the famous chronometer standard, defining strict accuracy under variance, forming the baseline for COSC certification. Finally, the NIHS 92-10 and 92-11 standards dictate synthetic sweat exposure and photochemical UV aging thresholds. Note that ultra-luxury brands often invent their own, exponentially harsher certifications like Meta's or the Rolex superlative chronometer, using these ISO standards merely as a starting baseline. Let us pause and review. We have completed Set 1. Look at the summary checklist on the left of your screen. What have we mastered so far? We defined habillage and identified its 13 core components. We explored the severe health risks associated with our materials, specifically the 10% prevalence of nickel/chromium allergies, the strict management of tritium radiation, and battery recycling mandates. We analyzed the grueling chemical constraints of atmospheric and liquid pollutants, and saw graphic evidence of sweat corroding solid steel. We mapped the physical constraints, surviving a 70 degrees Celsius temperature swing, UV degradation, 8000G kinetic shocks, and magnetic fields. Finally, we decoded the physics of water resistance, hydrostatic pressure, and the strict ISO standards that verify a case's integrity. Look at the right side. Coming up in Set 2, we will expand our terminology to 19 precise components. We will debate the kinematics of analog versus alphanumeric time displays. We will deconstruct the engineering of one-piece, two-piece, and three-piece case architectures, and conclude with a masterclass case study of the Jaeger-LeCoultre mastered chronograph. Take a short break. We will reconvene for Set 2. Welcome back to the lecture hall. We are now beginning Part 2 of Chapter 12. We are moving from the theoretical physics of environmental survival into the concrete realm of macroanatomy, display kinematics, and case architecture. Look at the 3D expanded blueprint on the screen. In this module, we will learn exactly how to name every single external interface component in both English and French. You cannot engineer a watch case if you do not speak the language of the manufacturers in Geneva and the Jura Valley. We will analyze the profound cognitive and mechanical differences between analog hands and alphanumeric digital discs. Why does the luxury industry still rely on a 13th century display technology? We will find out. Finally, we will tear down the physical architecture of the watch case itself. Look closely at the red Z-axis line on the blueprint cutting directly through the winding stem. This axis of power transmission represents the most vulnerable penetration point in the entire watch structure. How we build the case around this axis determines whether the watch survives a 300-meter dive or floods in the shower. Let's begin by building our professional vocabulary. Let's establish our structural nomenclature. Look at the habillage terminology diagram focusing on the external frontal interface, covering components 1 through 10. Study the cross-section on the right. 1. Trous de cadran, the dial holes. These precision-drilled apertures allow the central hand arbors to pass through the dial surface. 2. Cadran, the dial itself. The primary time display plate. 3. Guichets jour/quantum, day/date windows. Apertures cut into the dial to reveal the rotating indicator discs below. 4. Glacé avec bague, the crystal with its retaining bezel ring. The primary transparent armor. 5. Lunette carreur, the integrated bezel case middle. In this specific diagram, the top frame and middle chassis are machined from a single block of steel. 6. Encagage, the movement housing cavity. The precise volumetric void machine to hold the caliber. 7. Tube, the crown tube. This is a critical steel cylinder pressed into the case, acting as a guide and primary sealing housing for the stem. 8. Joint de fond de boîte, the caseback gasket. The vital elastomeric seal protecting the rear junction. 9. Pites de cadran, dial feet. The small copper or brass pegs on the back of the dial that lock it into the main plate. 10. Fond vis, the screw-in case back. Providing high-pressure rear hermeticity. Continuing our nomenclature, let's look at control and attachment, covering components 11 through 19. These are the operator interaction nodes and the strap attachment geometry. Look at the diagram on the screen. 11. Fond presse, a press-fit caseback. A snap-on closure relying on friction rather than threads. 12. Couronne, the crown. The primary winding and setting interface. 13. Poussoirs, pushers. These are external, protruding, finger-operated functional controls, typically for chronographs. 14. Corrector, a corrector. Unlike a pusher, this is a recessed button requiring a special stylus to press, preventing accidental changes to delicate calendar mechanisms. 15. Index de cadran, hour indices. The applied or printed markers on the dial. 16. Cellule d'affichage, display cell. An electronic LCD component if dealing with a hybrid caliber. 17. Entrecornes, the lug width. This is the precise metric gap between the horns. 18. Barrette, the spring bar. The telescopic pin holding the strap. 19. Bracelet, the strap or metal bracelet. Read the red critical specification box. The entrecornes, component 17, is an absolute, non-negotiable geometric dimension. It is rigorously machined to exact whole millimeters, usually 18, 19, 20, 21, or 22 millimeters. If this dimension is off by even a fraction of a millimeter, the spring bars will fail, and the watch will fall off the wrist. Now that we have identified the 19 components, we must classify them. Habillage is not a random collection of parts, it is a highly integrated machine. Let's review the Habillage system classification. Look at the 4 interlocking domains on the screen. System 1 is the dial and display interface. This includes the dial holes, the guichet windows, the indices, and the dial feet. Its sole purpose is communication. System 2 is the structural case, or the chassis. This includes the heavy armor, the bezel, the case middle, the caseback, and the internal movement cavity. It provides rigid physical protection. System 3 is sealing and interaction. This is the critical vulnerability zone. It includes the crystal, the crown tube, the crown, the pushers, and the correctors. Look at the warning note. Every single interaction point in System 3 represents a direct physical hole drilled through System 2. They are the gates that must be flawlessly sealed. System 4 is attachment geometry. This includes the lug width, the spring bars, and the strap, ensuring the entire mass remains securely attached to a human wrist in motion. When you design a watch, you are constantly balancing the conflicting demands of these 4 subsystems. Before we move into kinematics, I have provided you with the Master Habillage nomenclature matrix. Look at the bilingual table on the screen. This is your definitive reference standard for professional horology. I will not read every line again, but I expect you to commit this to memory. If you are working in a Swiss manufacturer, you will not ask for a watch glass, you will request le glacé. You will not discuss the dial legs, you will check the alignment of the pites de cadran. You will not measure the strap gap, you will caliper the entrecornes. Understanding the mechanical function column on the right is just as important as the translation. Notice how lunette carrure, number 5, explicitly defines a combined structural front frame and case body, whereas a standard carrure implies an independent middle section. Notice how a corrector, number 14, is functionally distinct from a poussoir, number 13, because one is recessed and one is external. Take a screenshot or photo of this slide. It is the vocabulary that separates the amateur enthusiast from the professional horological engineer. Let us transition from terminology to operation. We are looking at the kinematics of time display, operational theory. The primary, overriding mandate of a watch is the instantaneous communication of time. There are 2 fundamental engineering methods to achieve this. Look at the split diagram on the screen. Method 1 on the left is the analog display, or l'affichage analogique. This system relies on physical, rotating indicators, the hands sweeping continuously over a defined 360-degree stationary plane. It is driven by the classic motion works gear train beneath the dial. This is the oldest method, historically established in 13th century tower clocks, and standardized with 2 hands around the year 1700 following the invention of the balance spring, which finally made watches accurate enough to warrant a minute hand. Method 2 on the right is the alphanumeric display, or l'affichage alphanumérique. This system rejects sweeping hands. It relies on printed discs or rotating cylindrical rollers positioned strictly behind a fixed aperture window, or guichet. The characters pass the window sequentially, often utilizing complex jumper spring mechanisms to create a violent, instantaneous snap action step from one number to the next, exactly as a digital clock changes. Why does the luxury watch industry overwhelmingly favor the analog display? Because of a concept known as the cognitive superiority of the analog display. Look at the geometric breakdown on the screen. Read the text under the Trinity of Perception. In French horology, we call this un coup d'œil at a glance. Analog displays offer a uniquely rich, subtle perception that is neurologically impossible with standard digital numeric displays. In a fraction of a second, the geometry of the hands communicates three things simultaneously. 1. The current exact time. 2. The elapsed time, how much of the hour is gone. 3. The time remaining, the visual wedge of space left until the next hour. Look at architectural independence on the right. Hands convey highly accurate time through their relative angles alone. You can completely remove all numerals and markings from the dial, and the human brain can still instantly read the time. Furthermore, it holds universal language status. It transcends all alphabets and cultural barriers globally. It is a purely geometric, non-linguistic spatial code understood by everyone on Earth without translation. This is why analog remains the undisputed king of haute horlogerie. While analog is king, alphanumeric displays represent a massive engineering challenge. Let's examine the mechanics of discs and apertures. Look at the mechanical schematic on the right side of the screen. The engineering problem is complex. How do you translate the continuous, slow, creeping rotational force of the gear train into a sudden, discrete digital jump? Look at the components. The mechanism utilizes a star wheel, roue étoile, and a heavily tensioned jumper spring, ressort sautoir, riding against a specially shaped cam profile. Energy is slowly stored against the spring over 59 minutes. At the top of the hour, the cam tip passes the spring, releasing all that stored energy instantly, forcing the star wheel to violently snap forward exactly one discrete step. Read the design advantage box. Why use this? It provides a highly compact footprint. It eliminates the need for wide, sweeping perimeter minute tracks, allowing watchmakers to create purely dial-free, avant-garde aesthetic architectures. In haute horlogerie, we see this in jumping hours, saut DR, complications, retrograde sector displays, and highly complex, multi-axis mechanical printed roller drums. Let's synthesize these two philosophies using the display technology evaluation matrix. We are evaluating kinematic communication trade-offs. Look at the table on the screen. When we evaluate time reading speed, analog is the fastest for grasping elapsed or remaining time visually. Alphanumeric is the fastest if you only need the exact, instant numeric value. In terms of information density, analog is incredibly high, providing exact hours plus a relative spatial sense of the day. Alphanumeric is low, providing only the isolated numeric value. For cultural universality, analog is global. Alphanumeric is heavily dependent on the user's familiarity with specific Arabic, Roman, or regional numerals. Looking at movement complexity, analog relies on simple, continuous motion works gearing. Alphanumeric is vastly more complex, requiring high-torque jumping disc or roller drive mechanisms that drain mainspring power. Read the recommended resource callout at the bottom. If you want to see the absolute pinnacle of modern mechanical alphanumeric displays, I urge you to study the technical blueprints of the FP Journe Vagabondage series or the IWC Da Vinci. They are masterclasses in digital mechanical engineering. We leave the dial and turn to the structural integration of the chassis. Welcome to movement in cageage and the law of coaxiality. Look at the red vector line piercing the cross-section diagram on the screen. Fixation du mouvement à la boîte is the process of aligning the engine inside the chassis. Read the three pillars of movement fixation on the left. 1. Positioning in the x/y axis is dictated strictly by the encageage diameter, the outer edge of the movement matching the inner wall of the case. 2. Height in the z-axis is supported by the machined base support, the appui de bait. 3. Final fixation is achieved by driving heavy case screws, vis d'emboîtage, through the main plate directly into the case, or using dedicated clamps. But look at the red warning box on the right. This is the critical mandate, stem coaxiality. The height of the winding stem exiting the movement must be exactly identical to the height of the crown tube drilled into the case. Absolute, microscopic coaxiality is non-negotiable. If you are off by a fraction of a millimeter, forcing the stem through the tube will bend the stem, induce massive rotational friction, shred the delicate elastomeric O-rings, and guarantee a catastrophic failure of the watch's water resistance. A watch movement cannot simply be jammed tight against the inner walls of the case. We must manage spatial tolerances and internal clearances. Look at the two diagrams on the screen illustrating static space and dynamic oscillation. On the left, we see the rule for fixed components like the main plates and bridges. There is a strict, absolute minimum clearance of greater than or equal to 0.2 mm required between the rigid movement plate and the inner case wall. If the movement touches the wall, any impact on the outside of the case transfers 100% of its shockwave directly into the movement, shattering jewels. The 0.2 mm air gap is a vital shock buffer. On the right, we must account for dynamic components. Moving parts require massive expanded clearance envelopes to account for their physical sweep and kinetic expansion. Look at the red zones. The balance wheel needs oscillation clearance. The mainspring barrel physically expands outward as the spring is fully wound, requiring expansion clearance. And the automatic rotor requires a massive, unobstructed 360-degree sweep envelope. Furthermore, if you are encasing a quartz movement, you must machine dedicated cutouts to ensure the metallic battery contacts never touch the steel case wall, which would instantly short-circuit and ground the entire electronic system. What happens when your movement is 25 mm wide, but your marketing department demands a massive 42 mm case? You use the case ring solution, or circle de-emboutage. Look at the cross-section diagram on the screen. The shaded region filling the void between the movement and the outer case wall is the case ring. It acts as a structural intermediary, bridging massive dimensional mismatches. Look at the engineering purposes on the right. 1. Aesthetic architecture. It is absolutely essential for deliberate oversized design choices, which is extremely common today. Most brands use standard, small ETA or Celita calibers and house them in large, modern cases. 2. Restoration and retrofitting. In the rappellage or restoration sector, watchmakers must often machine custom case rings to safely fit alternative or replacement vintage movements into legacy cases where the original caliber is lost to history. Read the assembly requirement. Because the ring is an independent structural element, it introduces a new variable. It must be independently secured, perfectly leveled, and verified for concentricity before final torque is applied to the main case screws. Uneven torque here will physically warp the main plate, destroying the gear train's freedom of movement. Let us zoom out and look at macro case architecture. This is the foundational case equation, the 3+1 doctrine. Look at the exploded taxonomy on the screen. Despite the endless, bewildering array of aesthetic variations on the market, from square cases to octagons to asymmetrical avant-garde designs, every single watch case in the world manipulates the exact same primary structural elements. Read the 3+1 component doctrine. 1. The bezel, lunette the front retaining ring. 2. The case middle, carrure the massive, main structural chassis containing the movement. 3. The case back, fond the heavy rear sealing closure. And the +1 is the crystal, glacé the essential fourth element providing the transparent front shield. Look at the classification logic at the bottom. All modern case architectures, whether we classify them as monocoque, two-piece, or three-piece, are simply engineering variations of combining, separating, or permanently fusing these three specific metal elements to achieve different levels of cost, water resistance, and repairability. Let's examine these three architectures now. Architecture I, the monocoque or one-piece case. Look at the two diagrams on the screen. This design prioritizes absolute front-loading structural integrity. Read the structural definition. In a monocoque, the bezel, the case middle, and the case back are machined or molded as one continuous, unibody structure. There is no removable case back. The historical benchmark for this is the Swatch paradigm, maximizing mass-produced efficiency and eliminating rear water leaks entirely. However, look at the brutal assembly protocols and constraints. Because the back is solid, movement entry is strictly front-loading. The caliber must be dropped in through the bezel opening. How do you connect the crown if the movement is already buried inside a solid cup? Look at the bottom diagram. Stem engineering requires a specialized two-piece elastic stem assembly, Tigebrise. The outer stem is violently, elastically snapped into the inner movement receiver after encagage. Finally, crystal sealing. Look at the technical compression pliers on the bottom left. The watchmaker must physically crush the elastic synthetic crystal to temporarily reduce its diameter, plunge it into the case groove, crâne de glacé, and release it. Its violent outward expansion is the only thing sealing the case and locking the movement down. Architecture 2, the two-piece case. Look at the cross-section diagram on the screen. This is the absolute industry standard for mid-range horology and dress watches. Read the structural fit definition. The bezel and the case metal are permanently integrated into one unified component, the lunette carrure. The case back, however, remains independent and removable. Let's examine the key engineering features. Because the bezel is fixed, the crystal is permanently press-fit or cemented into the front groove. The rear access gives us two back closure options. Option 1 is the press-fit, fond presse. Look at the bottom left diagram. It utilizes an aggressive 80-degree conical taper to snap violently and securely into place via friction. Option 2 is the screw-in, fond vis. Look at the bottom right. The caseback is threaded directly onto the carrure, providing vastly superior structural compression against the rear gaskets for true water resistance. The engineering advantages versus monocoque are massive. The movement is directly accessible entirely from the rear without risking or removing the delicate front crystal seal. Furthermore, standard one-piece, solid steel winding stems can be safely utilized, eliminating the fragile snap-in stems. Architecture 3, the three-piece case. Look at the expanded diagram on the screen. This is the realm of uncompromising modularity and professional sealing. Read the structural definition. All three primary elements, the bezel, the case metal, and the caseback, are physically independent, heavily machined, separate components. The massive central carrure serves as the central anchor for the entire assembly. Look at the engineering advantages. Why go through the massive expense of machining three separate threaded components? First, maximum repairability. If a client heavily scratches the bezel against a brick wall, you do not have to replace the entire watch case. You simply unscrew the damaged bezel section, polish it, or replace it entirely independently. Second, ultimate sealing. This architecture offers the highest potential for redundant, multi-gasket sealing systems, crushing thick gaskets between heavy steel plates. This is vital for deep-sea diving watches. Third, design flexibility. It allows for swappable functional bezels like rotating tachymeters, dive scales, or gem set rings without redesigning or altering the main chassis. It is the undisputed architectural standard for luxury tool watches and haute horlogerie. Let us look at a master case study to see how a three-piece architecture is applied at the highest levels. Look at the blueprint of the Jaeger-LeCoultre master chronograph on the screen. This specific blueprint is a masterclass in reconciling intensely complex mechanics with absolute water resistance. A chronograph requires multiple buttons, meaning multiple gaping holes drilled directly into the waterproof chassis. Let's look at how JLC seals every independent penetration point. Coupe OA, crown sealing. Look at the top left. The diagram showcases the dynamic O-ring deeply compressed inside the heavy crown tube, maintaining a continuous friction seal even while the user is winding or setting the watch. Coupe OB, pusher sealing. Look at the top right. This details the independent gasket and heavy spring integration required to keep water out while the chronograph button is dynamically depressed underwater. Coupe OC, caseback sealing. Look at the bottom left. It illustrates the heavy threaded compression of the rear gasket, utilizing torque to create an impenetrable rear barrier. Coupe OD, crystal junction. Look at the bottom right. Notice the precision gasket seating within the independent, removable bezel structure, clamping the Sapphire down onto the middle case. To synthesize our architectural study, let's review the structural synthesis, case comparison matrix on the screen. This evaluates the harsh architectural trade-offs every watch design team must face. Compare the columns. Component integration, monocoque fuses all three. Two-piece fuses two. Three-piece separates all. Movement access, monocoque is a nightmare, requiring front/bezel side extraction. Two-piece and three-piece offer easy rear/back access. Water resistance. Monocoque is inherently limited by the elastic crystal seal. 2-piece is good, provided it uses a screw back. 3-piece is excellent, the absolute professional standard. Repairability score. Monocoque is low. If you damage the bezel, the entire watch case is ruined. 3-piece is maximum modularity. Stem requirement. Monocoque forces you to use the fragile 2-piece elastic snap stem. The others use robust standard solid stems. Crystal removal. Monocoque mandates ripping the crystal out for every routine service. The others leave the crystal safely undisturbed. The typical market application reveals the truth. Monocoques are relegated to fashion and budget tiers. 2-piece dominates the mid-range standard. And 3-piece completely owns haute horlogerie and professional dive categories. Let's transition to the workbench. This is the watchmaker's assembly and encageage protocol. Look at the strict sequential bench checklist on the right of your screen. When a master watchmaker finally mates the finished caliber to the case, they follow a rigid protocol. Step 1. Verify diameters. Ensure the movement encageage matches the case interior perfectly. If not, select and install the correct case ring. Step 2. Confirm coaxiality. Look at the digital micrometer on the left. The watchmaker measures the stem height. It must perfectly match the case tube Z-axis. Step 3. Check static clearance. Validate the absolute minimum 0.2 mm gap between fixed movement parts and the inner steel wall. Step 4. Check dynamic clearance. Rotate the watch 360 degrees to validate the expanded relief limits for the automatic rotor sweep, barrel expansion, and balance oscillation. Step 5. Torque hardware. Tighten the case screws or clamps evenly. Uneven torque will warp the brass plates and instantly stop the gear train. And finally, read the red mandatory box. Mandatory test. Conduct a pressurized dry or wet water resistance test post-assembly. If you skip this, you are delivering a defective product. To conclude set 2, we must understand the cascading consequences of violating these encageage protocols. Look at the failure diagnostics flowchart on the screen. Professional watchmaking is defined by absolute adherence to spatial geometry. The external heavy armor of the habillage cannot protect the internal engine if the integration protocols are violated. Let's trace the pathology. Read the Z-axis rule on the left. If you ignore a fraction of a millimeter mismatch in stem height, the solid steel stem will act as a miniature crowbar. As the user turns the crown, this misaligned lever will crush the delicate elastomeric crown tube O-ring on one side. This leads to the center box, crown stem friction and tube gasket abrasive wear. The rubber shreds. This inevitably leads to the red box on the right, total seal compromise, resulting in catastrophic water ingress. Look at the clearance rule in the bottom center box. Failure to maintain the 0.2 mm static gap results in microshocks transferring directly from the heavy steel case carrure into the delicate brass movement plates. This kinetic shock bypasses the Inca block system entirely, disrupting the escapement and potentially shattering the synthetic ruby jewel bearings. Geometry is survival. We will pause here. When we return for set 3, we will dive deeply into the microsealing systems, crown architectures, and the material science of sapphire crystals. Welcome back to the lecture hall, everyone. Please take your seats. We are now commencing part 3 of chapter 12, transitioning from the macro architecture of the watch case down into the microscopic realm. In the previous module, we looked at how cases are constructed in 1, 2, or 3 pieces, and how the movement is physically anchored within that chassis. Now, we must address the most vulnerable aspects of that chassis, the holes we intentionally drill into it. Please direct your attention to the blueprint on the screen. We are entering the domain of kinematic interfaces and microsealing systems. Look at the glowing red nodes on the 3D wireframe. These represent the interactive penetration points. To make a watch functional, we must provide the wearer with a way to wind the mainspring, set the time, and activate the chronograph. This requires physical steel shafts passing from the outside world, directly through the protective armor of the case, and into the delicate heart of the movement. How do we allow a steel shaft to slide and rotate freely while simultaneously blocking water molecules under intense hydrostatic pressure? This is the fundamental engineering paradox we will solve today. We will systematically deconstruct the architecture of the winding crowns, the pushers, and the correctors. Following that, we will examine the transparent armor, the crystals, analyzing the profound material differences between acrylic, mineral glass, and synthetic sapphire. Finally, we will dive deep into the chemistry and physics of the microsealing technologies themselves, exploring elastomeric gaskets and anaerobic structural adhesives. Your mastery of these components will determine whether your watch survives a dive to the ocean floor or perishes in a simple rainstorm. Let us begin. Let us begin our analysis with the most ubiquitous and historically significant kinematic interface on the watch, the winding crown, or la couronne de remontoir. Look at the cross-sectional diagram on the screen, paying specific attention to the glowing red z-axis representing the winding stem. I call this the engineering paradox. Read the core kinematics on the right. The crown serves multiple dynamic functions. In its resting state, position 0, it must transmit purely rotational drive to wind the mainspring. However, it must also accommodate lateral, axial displacement. The user must be able to pull the crown out to position 1 for the quick set date, position 2 for time setting, and perhaps even a position 3 for other complications. Now, read the absolute law in the orange warning box. The rigid steel shaft, the tige de remontoir, must physically breach and pass completely through the lateral wall of the case metal, the carrure. There is no wireless transmission of mechanical torque, there must be a physical connection. This creates our ultimate vulnerability. If we fail to perfectly seal this dynamic, moving joint, the watch is immediately compromised. Capillary action will pull moisture, microscopic atmospheric dust, and textile fibers directly into the caliper. The consequence of this is not just a dirty movement, it is the instant degradation of the synthetic microlubricants on the pivots, and the rapid onset of ferrous oxidation, rust, on the steel pinions. Sealing the crown is not an afterthought, it is the primary defensive engineering challenge of the entire habillage system. To understand modern sealing, we must first look at the historical baseline. This is the unsealed architecture, or the non-waterproof crown. Look at the two diagrams on the screen. On the left, we have a solid type crown, on the right, a hollow or EVA D type. Let us analyze the construction mechanics. In both designs, the cylindrical bore of the crown, known as the cannon, is simply inserted directly into an aperture drilled into the case metal. How does it rotate? It operates purely on a standard clearance fit, or jus. There must be a microscopic gap between the steel of the crown cannon and the steel of the case wall to allow free, frictionless sliding and rotation. Notice what is missing. There are absolutely zero elastomeric sealing elements. There is no rubber, no silicone, no barrier whatsoever. Look at the operational limitations in panel 3. Because of this necessary clearance gap, this design offers absolutely zero resistance to capillary action. If a single drop of water hits that gap, it will be sucked directly into the movement. Furthermore, it cannot block fine atmospheric dust. Therefore, this architecture is strictly limited to formal, ultra-thin dress watches, or historically, vintage pocket watches that were never intended to be exposed to the elements. Today, if you are designing a sports watch, utilizing this unsealed architecture is considered professional negligence. You must upgrade to dynamic sealing. When clearance fits fail against the environment, we must introduce elastomers. Welcome to dynamic radial sealing, the O-ring waterproof crown. This is the absolute industry standard for the vast majority of wristwatches produced today. Look at the kinematic architecture on the screen. Notice the fundamental structural difference from the previous slide. We no longer simply drill a hole in the case. Instead, we utilize the tube. This is a highly specialized, polished steel guide cylinder, the tube de couronne, which is aggressively press-fit, or chassé, into the case metal. Now, look at the red component, the pivot. This is an elastomeric O-ring, or joint torique. It sits securely inside the crown cannon. When the crown is pushed over the tube, the O-ring is compressed between the inner wall of the crown and the outer polished wall of the tube. Read the radial seal physics box. Because the O-ring is squeezed radially, it provides continuous friction and compression against the smooth tube wall. As the user rotates the crown in position 0 to wind the watch, the rubber simply slides along the polished steel, maintaining a perfect, watertight barrier. This architecture easily achieves standard 3 to 10 ATM water resistance ratings. However, read the kinematic vulnerability at the bottom. When the user pulls the crown out to set the time, the O-ring slides laterally outward. The sealing efficacy drops significantly during this axial displacement. Furthermore, this seal is prone to friction wear over years of constant winding. It is a consumable component that requires vigilant maintenance. When human lives depend on the watch, standard dynamic friction is insufficient. We must achieve deep water resistance using the screw-lock crown. Look at the heavy-duty schematic on the screen. This is the architecture mandated by the ISO 6425 standard for professional diving watches. Let us examine the mechanism of action. Notice the aggressive machining on the components. The internal walls of the crown and the external walls of the tube now feature corresponding, heavy-duty threads. The user must push the crown inward against a heavy spring and physically screw it down onto the case. Look at the dual sealing strategy box. This is where the genius lies. First, we still maintain the radial dynamic seal. We still have internal O-rings handling standard friction sealing when the crown is unscrewed for winding. But second, and most importantly, we introduce extreme axial compression. Look at the glowing red flat gasket at the roof of the crown interior. As the user cranks the threads down, this flat elastomeric gasket is brutally crushed between the roof of the crown and the flat top edge of the steel tube. This mechanical thread locking creates an impenetrable, high-pressure hermetic seal that actively fights back against the crushing hydrostatic pressure of the deep ocean. But heed the performance and vulnerability warning. This massive mechanical lock prevents accidental snagging underwater, allowing ratings from 10 ATM all the way to 300 plus ATM. However, its critical failure point is purely psychological. It relies entirely on user compliance. The crown must be manually locked down prior to immersion. If the diver forgets to screw it down, the watch will flood instantly. In haute horlogerie, we face a unique problem. Raw, machined steel threads are not aesthetically acceptable on a luxury timepiece. We must master aesthetic integration, crown caps and cabochons. Look at the beautifully finished crown on the screen. We are concealing heavy industrial infrastructure beneath a luxury exterior. Let's discuss precious metal caps, or coiffes. Read the engineering rationale. Solid, high-carat gold, like 18K yellow or rose gold, is incredibly soft. If we machined the internal screw threads directly into solid gold, the repeated shear stresses of the user aggressively tightening and untightening the crown over decades would strip the threads completely, destroying the seal. The solution? We utilize a hardened stainless steel core, which holds the durable threads, and we envelop it in a thin, permanently bonded gold cap. This perfectly balances the structural yield strength required for water resistance with the luxury aesthetic demanded by the brand. Now, look at the cabochon setting techniques on the right. A cabochon is a polished, unfaceted gemstone, typically sapphire, spinel, or onyx, set into the flat outer end of the crown. These are secured via precision structural bonding or delicate bezel setting into a machined metal lip. But read the hermetic challenge at the bottom. The adhesive or setting technique utilized must absolutely not introduce a microscopic cavity or moisture trap that bypasses the primary crown seals. Water can sometimes wick under a poorly glued cabochon, causing hidden corrosion from the outside in. Every aesthetic choice has an engineering consequence. We must now look at the secondary kinematic interfaces, pushers, or les poussoirs. Every pusher added to a case is a new, independent atmospheric vulnerability that must be managed. Look at the three diagrams on the screen. Let's establish the definition. Pushers are protruding, tactile buttons projecting outward from the case metal, designed strictly for direct, manual finger operation. We see them predominantly on chronographs and mechanical alarms. Their kinematics rely on a spring-loaded return mechanism. The user's depression drives an internal lever into the movement. Releasing the finger allows the heavy internal spring to instantly reset the button's position. Look at the structural variations on the left. First, we have the cylindrical pusher, a simple, elegant tube. Second, we have the shouldered pusher, or apporti, which features a stepped structural ledge to prevent the button from being accidentally ripped out of the case. Now, read the water resistance logic at the bottom, and look at the internal mechanics diagram on the right. Every individual pusher requires its own independent internal O-ring, or joint torique. This O-ring must slide dynamically over the highly polished pusher shaft every single time the chronograph is activated. If you actuate a chronograph while submerged underwater, the dynamic movement of the shaft can actually drag water molecules past the O-ring. This is why most manufacturers strictly forbid operating pushers underwater unless they utilize highly specialized, complex magnetic or secondary sealing systems. What if we have a delicate complication, like a perpetual calendar, that requires adjustment, but we absolutely cannot risk the user accidentally bumping a pusher and advancing the date by a month? We utilize recessed actuation, correctors, or less correctors. Look at the cross-sectional diagrams on the screen. Read the definition. Correctors are flush or deeply recessed buttons that are fully embedded within the profile of the case middle. They are strictly tool-operated. You cannot press them with your finger. They require a specialized stylus or pointer to actuate. Look at the two variations. We have the cylindrical corrector on top, and the shouldered corrector, correcteur à portée, on the bottom. Notice how the internal return spring and the sealing O-rings are identical in principle to the pushers we just studied. The physics of sealing the shaft remain exactly the same. However, read the engineering advantage at the bottom. Because they are recessed flush with the metal, it is physically impossible to activate them accidentally via a violent wrist impact or by catching them on clothing. Furthermore, from an aesthetic standpoint, they offer a completely clean, unbroken case profile. When a grand complication requires 6 different adjustment points, covering the case in protruding pushers would ruin the visual elegance. Correctors provide the necessary interface while maintaining absolute architectural purity. To solidify your understanding of these external controls, let us review the actuator diagnostic matrix, pushers versus correctors. As a case engineer, you must select your interfaces based on a strict calculation of risk and intended application. Look at the table on the screen. Compare the profiles. A pusher, poussoir, protrudes outward, while a corrector, correcteur, is flush or recessed. Compare the actuation method. A pusher requires direct, heavy finger operation, relying on instant tactile feedback. A corrector requires a specialized tool, demanding deliberate, slow, considered action. Now, compare the accidental activation risk. For a pusher, the risk is exceptionally high. It is exposed to direct wrist impact during sports or daily wear. For a corrector, the risk is practically zero, it is physically impossible to snag on a doorframe. Finally, look at the typical applications. Pushers belong on fast action devices, chronographs and mechanical alarms. Correctors belong on delicate, slow-moving mechanisms, perpetual calendars, moonphase, and complex electronic adjustments. Read the design imperative at the bottom. Both interfaces demand independent elastomeric shaft sealing. However, pushers introduce severe dynamic operational risks during intense physical activity, whereas correctors isolate the user's inputs to safe, controlled maintenance interactions on a desk. Choose your actuator based on the lifestyle of the complication it controls. We now shift our focus from the side of the case to the top. We must examine the transparent armor, synthetic crystals, specifically PMMA, or acrylic. Look at the installation sequence on the screen. This is a masterclass in utilizing material memory. Why use plastic on a watch? Acrylic, historically known as hezolite, is a tender, highly elastic polymer. Its greatest engineering advantage is its exceptional impact resistance. It is virtually shatterproof. If struck violently, it bends and dents, but it will not explode into razor-sharp shards that could fall into the gear train. This is exactly why NASA mandated hezolite for the Omega Speedmaster on the Apollo missions. However, look at the assembly process. Because it is highly elastic, we secure it using material memory expansion. Step 1. The watchmaker uses a specialized, multi-pronged tool to radially compress the crystal's perimeter. Step 2. This violent compression temporarily reduces the outer diameter of the dome via elastic deformation. Step 3. The shrunken crystal is inserted directly into the undercut case groove, the cran de glace. Step 4. The tool is released. The polymer violently attempts to return to its original shape, expanding outward with massive force, creating a totally waterproof friction fit against the steel wall. Look at the diagram on the right. To further reinforce this against deep hydrostatic pressure, we often press a metal tension ring, or armée, into the inside lip of the crystal. This ring actively and permanently presses the polymer outward, massively reinforcing the seal. It is a brilliant use of polymer physics. While acrylic is shatterproof, it is incredibly soft and scratches easily. As consumer demand for scratch resistance grew, the industry transitioned to rigid barriers, specifically mineral glass. Look at the cross-section on the screen. We must now manage inelasticity. Read the inelasticity problem on the left. Tempered mineral glass possesses near zero elasticity. It absolutely cannot be radially compressed by a tool. If you attempt to force or press fit a rigid glass disc directly into a raw steel groove, the brutal metal-on-glass contact will result in catastrophic edge chipping or concentric pattern shattering. The entire crystal will explode under the press. Therefore, look at the mounting requirements and the diagram. Because the glass cannot flex, we must secure it using highly compressible secondary intermediaries. The primary method, shown in glowing red on the schematic, utilizes an L-shaped synthetic gasket, often called an eye-ring. This gasket is seated into the bezel, and the rigid flat crystal is pressed smoothly into the gasket. The gasket takes 100% of the compression force, protecting the glass edge while sealing the gap. The secondary method is purely chemical. We utilize structural UV curing adhesives to create a continuous, liquid chemical bed that hardens, locking the glass to the steel without any mechanical crushing force. You must respect the brittleness of silica. Today, in haute horlogerie, we accept only the absolute pinnacle of transparent armor. Welcome to the Sapphire standard. Look at the material science profile on the screen. We are dealing with optical perfection and extreme hardness. Read the material science profile. What we call sapphire crystal in watchmaking is actually synthetic monocrystalline aluminum oxide, Al2O3. It is grown in laboratories via the Verneuil or Czochralski processes. Its engineering constraints are terrifying. Because of its extreme hardness, it cannot be molded, stamped, or conventionally cut. It can only be machined, sliced, and polished using industrial diamond tooling. This vastly increases production costs and lead times. Look at the central diagram showing the reflections. Untreated sapphire is highly reflective, bouncing about 8% of light back at the wearer, making the dial unreadable in bright sun. Therefore, we apply anti-reflective, or AR, coatings. Microscopic layers of magnesium fluoride, MgF2, are vapor deposited onto the surface, dropping reflection to under 0.5%. But heed the coating durability warning on the right. Bare sapphire is completely immune to standard surface scratching. However, the AR coating layers are much softer, closer to mineral glass in hardness. When a client complains that their sapphire crystal is scratched, 99% of the time, the sapphire is perfectly intact. It is the microscopic AR layer that has been gouged. To solve this paradox, many luxury manufacturers now refuse to coat the top of the crystal, limiting AR coating strictly to the internal underside surface where they cannot be touched. To truly understand why sapphire dominates the luxury market, we must quantify durability. Let's examine the material science spectrum, crystal hardness and scratch resistance. Look at the comparative scales on the screen. We measure hardness scientifically using the Vickers scale, HV, and the Mohs scale of mineral hardness. Look at the top graph. Synthetic acrylic sits at a pathetic 20 to 30 HV. It is incredibly soft. Mineral glass represents a massive leap, sitting between 500 and 800 HV. It is respectable for daily wear. But look at the yellow bar for sapphire. It registers an astonishing 2000 to 2200 HV. Now, translate those numbers into the scratch vulnerability profile at the bottom. Acrylic, Mohs 3, will be deeply scratched by ordinary coins, keys, or just rubbing against a desk edge. You must polish it weekly with Polywatch. Mineral glass, Mohs 5 to 6, easily survives keys and coins, but it will be immediately scratched by sand, quartz dust, or brushing against a masonry brick wall. Sapphire, Mohs 9, is practically invincible. The only materials commonly encountered on Earth that can scratch it are diamond or silicon carbide. You can take a steel nail to a sapphire crystal, and it will not leave a mark. This guarantee of eternal, pristine clarity justifies the immense manufacturing cost. We have covered the hard armor. Now we must study the soft tissues that hold it all together. Welcome to microsealing technologies, the geometry of elastomers. Look at the three red cross-sections on the screen. Read the text on the right, the physics of compression. Horological sealing does not operate on permanent brute crush force. It operates strictly on continuous elastic memory. Elastomers function by constantly attempting to return to their original geometry. When you squeeze them into a gap, they generate persistent, microscopic counter pressure against the metal walls, blocking water molecules. Let's look at the typology applications of the three shapes. First, the O-ring, or joint torique, on the left. This circular cross-section is the absolute industry standard for dynamic rotational and axial sealing. This is what you find inside crown tubes and pusher shafts. It rolls and compresses beautifully. Second, the flat gasket, or joint plat, in the center. This is primarily used for static sealing under extreme, uniform axial compression. You will find massive flat gaskets crushed under the screw-down casebacks of deep-sea diving watches. Third, the formed gasket, or joint deformé, on the right. These are custom, specialized profiles engineered to fit specific, non-circular geometries, like rectangular casebacks or complex crystal seating grooves where standard O-rings would pinch or fail. Elastomers are miraculous, but they are not immortal. Let's examine gaskets, degradation mechanisms, and professional maintenance. Look at the diagrams illustrating the inevitable collapse of elastic equilibrium. Read the mechanisms of physical degradation on the left. The most fatal, silent killer is compression set. Over years of being squeezed under high pressure, the elastomer undergoes permanent deformation. It flattens out. It loses its vital ability to spring back against the metal walls, quietly destroying the water resistance from the inside. The second killer is chemical swelling. The rubber absorbs microscopic amounts of cleaning solvents, human sweat, aggressive sunscreen, and seawater, causing the polymer chains to bloat and break down. The third is thermal and ozone aging. Constant exposure to UV light and temperature swings causes the surface of the gasket to harden, crack, and lose all tensile flexibility. Because of this, look at the mandatory professional maintenance protocol on the right. Visual inspection is totally insufficient, microcracks are often invisible to the naked eye. The rule is absolute: you must replace caseback and crystal gaskets routinely during every full service. You must utilize the exact OEM cross-section diameters. Using a generic gasket that is 0.1 mm too thin will ruin the mathematical compression forces. Finally, you must meticulously lubricate dynamic seals with specialized synthetic silicone grease, like Molykote 111, to reduce rotational friction wear. Dry rubber tears, lubricated rubber seals. When elastomers cannot solve the problem, we turn to chemistry. Let's look at chemical fastening, adhesive fixation versus structural sealing. We are deploying highly specialized polymers in horological habillage. Look at the two distinct roles on the screen. Adhesives serve dual roles in habillage. On the left, the fixation interface. We use adhesives to mechanically lock threaded components together. For example, bonding the crown permanently to the winding stem. If this bond fails, turning the crown counterclockwise to set the time would simply unscrew the crown right off the stem, causing a catastrophic detachment. On the right, the sealing interface. Adhesives create an impenetrable, continuous environmental barrier where elastomers are geometrically unsuitable, such as securing irregular-shaped mineral glasses into complex bezels. To achieve this, we rely heavily on the science of anaerobic adhesives, famously known by the brand name Loctite. Read the curing trigger carefully. These are liquid monomers that polymerize into a tough, thermoset plastic only upon two strict conditions: the total absence of oxygen and physical contact with active metal ions. This dictates a vital storage imperative: the bottles you keep on your bench must permanently remain half full of air. If you vacuum seal a bottle of Loctite, the lack of oxygen will cause the entire bottle to spontaneously cure into a solid block of plastic overnight. You cannot just grab superglue and build a watch. Let's review the engineering matrix, adhesive selection, and chemical hazards. Look at the precise chemical mapping table on the screen. Different applications demand totally different chemistries. For the crown to stem bond, you need high shear strength, but it must be heat removable for future servicing. We use anaerobic thread lockers, like Loctite 243 or 271. For crystal to case bonding, you need zero outgassing, total optical clarity, and UV stability so it doesn't turn yellow in the sun. We use specialized UV curing acrylics. For a caseback edge seal on a vintage piece, you need gap-filling high flexibility. We use silicone RTV sealants. For dial feet securing, you need extremely low strength so the dial can be mechanically broken free later without snapping the copper feet. We use anaerobic low strength, like Loctite 222. Now, read the critical assembly warnings in the hazard box. First, excess UV adhesive expanding past the crystal joints will cause severe, irreparable optical distortion. You must use microscopic precision. Second, and most importantly, cyanoacrylate common superglue must never be used anywhere near a watch assembly. Its aggressive outgassing vapors will instantly cause blooming. This means it will permanently cloud the underside of the sapphire crystal with a white haze, and the fumes will chemically dissolve and destroy the movement's microscopic oil reserves. Never use it. We have analyzed every individual seal, gasket, and adhesive. Now, we must put them all together. Let's review system synthesis, the holistic barrier and total integration. Look at the magnificent 3D mapping of the 7 critical penetration points on the screen. A waterproof watch is essentially a miniature submarine. Let's trace the boundary. 1. The front, the crystal to bezel junction, sealed via UV adhesive or an eye-ring. 2. The upper frame, the bezel to case middle junction, sealed via an O-ring or cement. 3. Side control 1, the crown stem to tube, sealed via dynamic O-rings. 4 and 5. Side controls 2 and 3, the chronograph pushers, each sealed via independent dynamic O-rings. 6. Side control 4, the recessed corrector, sealed via its own dynamic O-ring. 7. The rear, the case back to case middle junction, sealed via a massive static flat or O-ring gasket. Read the chain of vulnerability on the left. Water resistance is an absolute binary state. A watch is either 100% sealed, or it is flooded. The unified atmospheric system of the interior is only as strong as its weakest microscopic seal. If the front crystal is perfectly bonded, but a single microscopic O-ring and pusher B suffers compression set, the entire inner atmosphere is compromised. The entire system fails as one. When the system fails, you must know how to fix it. Let's look at post-service protocols and diagnostic troubleshooting. Review the symptom isolation guide on the screen. If a client brings you a watch with fogging under the crystal, the most likely failure point is crystal gasket or cement degradation. You must completely remove the crystal, scrape the old adhesive, and reseal it. If you see corrosion on the crown area, the crown O-ring has suffered mechanical wear. You must extract the stem and replace the O-ring deeply inside the tube. If there is a water trace specifically from the back, the caseback gasket has suffered compression set. Replace the static gasket and test the torque. If the dial is mysteriously yellowing but there is no water entry, you have gas pollution. Someone previously used the wrong adhesive, and it is outgassing. You must audit the chemical environment. Now read the mandatory post-service protocol governed by ISO 22810. When you finish a repair, you do not just guess that it is sealed. You must replace all static and dynamic gaskets regardless of their visual condition. You must lubricate the dynamic seals with specialized silicone grease to eliminate dry friction tearing. And finally, you must perform a hydrostatic pressure test to 125% of the rated depth to ensure an absolute safety margin before the watch ever touches the client's wrist. Hermeticity is a fragile, temporary equilibrium. Continuous, rigorous maintenance is non-negotiable. We have reached the end of part 3. Let's consolidate the Habillage defense systems we have just studied. Review the Set 3 summary and key engineering principles on the screen. 1. Crown evolution. We traced the path from the historically vulnerable non-waterproof clearance fit, up through dynamic O-ring friction seals, culminating in the absolute security of deep-sea ISO 6425 screw-lock thread compression systems. 2. Kinematic actuators. We distinguished between pushers, which use spring returns and require highly vulnerable isolated O-rings, and correctors, which are flush-mounted for tool-only operation, ensuring zero risk of accidental wrist impacts. 3. Transparent armor. We learned that acrylic utilizes elastic memory for brilliant snap fits, while mineral and sapphire possess near zero elasticity, absolutely demanding highly compressible synthetic intermediaries or structural cements to prevent shattering. 4. Material imperatives. We established that sapphire represents the ultimate barrier. At Mohs 9 and 2000 Vickers, it is practically scratch-proof against all standard earthly abrasives, though its crystalline structure remains susceptible to localized brittle edge impacts. 5. Gasket geometries. O-ring, flat, and formed gaskets operate strictly on the physics of continuous elastic memory. Compression set and chemical swelling are the primary, silent failure mechanisms. 6. Chemical fastening. We explored how anaerobic adhesives serve dual fixation and sealing roles, requiring the total absence of oxygen in contact with active metal ions to successfully polymerize into thermoset plastics. Take a deep breath. When we return for our final module, Part 4, we will explore the artistic and metallurgical mastery of dials, hands, case materials, and straps. Welcome back, engineers. We have finally reached the culmination of our study. This is Chapter 12, Part 4, Dials, Hands, Case Materials, and Attachments. Please direct your attention to the final exploded blueprint on your screen. Up until now, our entire focus has been on defensive engineering, building an impenetrable fortress to protect the movement from water, shocks, and chemistry. But habillage is not just armor, it is the face of the watch. It is the sole medium through which the mechanical genius of the caliber communicates with the human wearer. Look at the spec box on the right. In this final module, we will dissect the interface. We will examine the micromechanics of dial construction, fixing mechanisms, and the high-precision art of typographic marking. We will then analyze the kinematic indicators, the hands. We will study hand typology, the kinetic physics of rotational inertia, and the structural engineering of arbor fixing cannons. Following that, we dive into material science. We will explore the strict legal frameworks governing noble metals, the industrial reality of stainless steel and brass, and the bleeding-edge shrinkage physics of high-tech ceramics like zirconium dioxide. Finally, we will conclude with wrist attachments, ensuring the entire massive assembly remains safely secured to the human body via integrated architectures and microscopic spring bar linkages. Let us cross the finish line. We begin with the canvas of time, dial architecture. Let's look at fundamental construction and microfixation. How exactly do we attach a delicate brass plate perfectly to the main movement plate without crushing the gear train? Look at the three engineered solutions on the screen. Read the spec box. The base material is almost exclusively a brass plate, or plaque de laiton. It is machined perfectly flat, or sometimes domed bomb, to accommodate the sweeping profiles of the movement hands beneath it. It is precisely aligned to the main plate using delicate copper or brass pegs called dial feet, or pites de cadran. How do we lock those feet down? Method 1 on the left is the screw method. This is rigid. Tiny set screws are threaded directly into the side of the main plate, biting into the soft copper dial foot. It is extremely rigid, adjustable, and completely secures against high G shocks. It is the absolute standard for haute horlogerie. Method 2 in the center is the synthetic insert snap fit. Elastic nylon or PA66 inserts are pressed into the main plate. The dial feet simply snap into them. It allows for incredibly fast assembly, absorbs minor vibrations, and is highly optimized for mass-produced, automated assembly lines. Method 3 on the right is the clamp method. Massive metal clamps, brides de serrage, overlap the dial edge or bite into a specific groove, distributing clamping pressure evenly. This is generally reserved for massive pocket watch movements or highly specialized, non-standard geometries. The dial cannot be a solid plate, it must allow information to pass through it. Let's look at dial apertures, accommodating kinematics and displays. Look at the complex geometric blueprint on the screen. Dials must be precisely pierced, utilizing trews de cadran, to interface flawlessly with the movement beneath. On the left, we have hand arbors, or axes. You have the central holes for the concentric alignment of the hour, minute, and central chronograph seconds arbors. You also have subdials, offset holes for running seconds or power reserve indicators. Read the yellow tolerance critical warning. The central hole must clear the spinning cannon pinion perfectly to prevent any rotational friction. However, the hole must remain incredibly tight, often with tolerances of plus or minus 0.01 mm, to avoid exposing the raw, unfinished brass main plate lurking just beneath the dial. On the right, we have windows, or guichets. These are openings designed to reveal the alphanumeric or graphical discs rotating beneath the dial. We have standard rectangular windows for the date, quantime, and day. We have highly complex curved or semicircular apertures for moon phases, retrograde indicators, or wandering hours. And in modern haute horlogerie, we see entirely custom geometries tailored to specific caliber architectures, such as massive double-date trapezoidal frames. The dial aperture is where analog plates meet digital discs. Once the holes are cut, we must apply the information. Let's review typographic and index integration. Look at the three primary methods for applying ink and metal to the brass base on your screen. Method 1 is transfer or pad printing, decalc. This is the industry standard. A soft silicone pad, the tampon, picks up wet ink from an etched steel cliché and presses it directly onto the dial. It achieves incredibly fine, microscopic lines, like precision minute tracks. Because the ink is pressed hard, it creates the optical illusion of ink printed deeply into the dial, and it conforms perfectly to heavily textured gouache surfaces. Method 2 is screen printing, serigraphy. Ink is forced through a highly tensioned fine mesh stencil using a squeegee. It deposits a much thicker, physically elevated layer of ink. It is ideal for laying down highly opaque solid colors or building up thick bases for luminous paint. Method 3 represents applied indices, or index appliques. These are physical, dimensional hour markers that add depth, catch light reflections, and massively elevate the perceived luxury value of the dial. Look at the structural options. You can use pin fixing, goupillage, where micropins on the back of the index pass through drilled dial holes and are riveted tight. This offers maximum security against high G-shock. Alternatively, you can use adhesive bonding, gluing them directly to the surface, or embossing, matrices, where the index is literally stamped up out from the brass base material itself. Finally, these indices are diamond polished, faceted, and often filled with superluminova. The base brass must be transformed into a luxury surface. Welcome to Surface Mastery, Chemical and Optical Dial Finishing. We are manipulating light behavior through advanced material science. Look at the four primary techniques on the screen. Method 1 is galvanic treatment, traitements galvaniques. This involves electroplating the raw brass with precise, microscopic layers of precious metals like gold, silver, rhodium, or ruthenium. It creates brilliant metallic bases and is the standard application placed over deep engine-turned gouache engravings to protect the cuts while adding luster. Method 2 is varnishing or lacquering, vernissage. Translucent or highly opaque colored lacquer is applied directly over a base galvanic protective layer. It offers an endless color matrix. Physically, it seals and protects the underlying delicate galvanic layers from atmospheric oxidation and moisture damage. Method 3 is vapor deposition, specifically PVD or CVD. We vaporize solid metal in a vacuum chamber and bond it at the molecular level. It yields ultra-durable, microscopic color layers that perfectly preserve the physical grain or polish of the dial without filling in the texture like thick paint would. Finally, Method 4 is the legendary Grand Fou enamel. Silica glass powder is meticulously applied to a raw copper base and kiln-fired repeatedly at temperatures exceeding 800 degrees Celsius. It offers supreme, unmatched optical depth and is completely fade-proof for centuries. However, read the tolerance critical warning. The failure rate, cracking, bubbling, or warping during production is extremely high, restricting this purely artisanal method to ultra-premium haute horlogerie. We move from the stationary dial to the dynamic indicators. Let's study kinematic indicators, proportions and inertia. Look at the physics diagram of the micro lever on the screen. Read the quote at the top, "Hands are not mere indicators. Their form and appearance contribute, like all habillage components, to creating the style of the watch. But style must bow to physics." Read the engineering imperative. Hands are rotational microlevers battling violent physics. During severe accelerations, such as a chronograph hand instantly snapping back to zero, or an 8000 G drop impact, violent rotational kinetic inertia attempts to overcome the friction grip of the hand's arbor. The structural interface must hold perfectly. If the hand shifts its alignment on the arbor by even 0.1 millimeters, the timing display is permanently ruined. Now look at the proportional and stylistic rules on the right. These are the golden ratios of dial design. The hour hand, aiguille d'Ars, is mathematically designed to be generally 20% shorter but visually wider and heavier than the minute hand. This distinct disproportion ensures instant, unambiguous cognitive recognition at a glance. The minute hand is longer, reaching precisely to the inner edge of the printed minute track, but with a narrower aerodynamic profile to reduce the torque load dragging on the center wheel. These rules adapt to the design archetypes. Technical instruments demand simple, high-contrast, luminous forms optimized for instant legibility. Classic dress watches demand artistic, refined, heritage-inspired forms to project elegance. Let's look at those specific forms next. You must learn the vocabulary of design. Let's review classic hand typologies, form and function, part 1. These are the foundational geometries of modern watchmaking. Look at the 3 blueprints on the screen. First is the alpha hand. Visually, it features a wide base near the center arbor, tapering sharply in a straight line to a fine-pointed end. Application-wise, it was the elegant standard for mid-century sports and dress watches. Its wide, flat facets provide excellent surface area for high-polish finishing, catching light beautifully. Second is the batten hand, or batten. Visually, it is exactly as it sounds, straight, parallel sides terminating with a flat or gently pointed tip. Application-wise, it is the cornerstone of modernist, Bauhaus, and contemporary tool watches. It is highly legible, structurally robust, and exceptionally easy to fill with massive amounts of luminous material. Third is the legendary Breguet hand. Visually, it features an eccentric, hollowed-out ring, often called a moon or apple, near the tip. Application-wise, it is the absolute symbol of traditional haute horlogerie. Invented by Abraham Louis Breguet in the late 18th century, the genius of the design is that the hollow tip allows the underlying numerals on the dial to be read perfectly through the hand without physical obstruction. It is a masterpiece of functional elegance. Continuing our design vocabulary, let's look at classic hand typologies, form and function, part 2. Here we see dramatic profiles, organic curves, and needle precision. Look at the 4 blueprints on the screen. First is the Dauphine hand. Visually, it is strongly faceted, featuring a distinct triangular profile tapering sharply to a point. Because it is heavily ridged down the center, it is highly reflective and dramatic. It remains the absolute standard for 1950s dress watches like the Patek Philippe Calatrava. The center facet dynamically catches light from multiple angles, ensuring legibility even in dim restaurants. Second is the leaf hand, or faille. Visually, it features organic, flowing curves that swell gracefully in the middle and narrow to a fine point at both the base and the tip. It is understated, utilized in dress pieces requiring a softer, more fluid visual integration with the dial. Third is the sword hand, or glaive. Visually, it features a pronounced wide blade that maintains its thickness before sharply tapering right near the tip. It is structurally massive, making it excellent for holding immense volumes of luminous infill in pilot and military dive watches. Fourth is the lance hand. Visually, it is highly slender, featuring a needle-like main body terminating in a distinct, widened arrowhead tip. It provides elegant, historical precision, offering a highly exact pointing indicator with a distinctive end profile, often seen in high-end chronographs. Finally, we must recognize the outliers and the icons. Let's review antique typologies and modern proprietary signatures. Look at the specific geometries on the screen. On the left, we have the classical conclusion from the pocket watch era. The pear hand, or pour, features a distinctive bulbous swell just before the tip. It is heavily featured on vintage pocket watches and antique marine chronometers. The Roman hand, romaine, is highly angular, pointed, and features stepped sections, reminiscent of Baroque architecture. The Louis XV and XVI hands feature highly ornate Rococo openwork or restrained neoclassical geometries. They are beautiful but incredibly fragile and difficult to read. On the right, we have modern proprietary functional signatures. These are geometries originally engineered for strict mechanical purposes that evolved into recognizable brand icons. Look at the Rolex Mercedes hand. The engineering purpose of that 3-pointed star is crucial. The matrix physically holds a massive, high-volume plot of brittle luminous material, 4.50 mm in diameter, in place. The structural struts prevent the fragile lacquer from cracking and falling out under physical shock. Look at the Tudor snowflake hand. The engineering purpose was maximized surface area, a massive 2 mm square, for extreme underwater legibility, while providing absolute, instantly recognizable anti-glare distinction from the minute hand. And the IWC Portuguese hand features an optimized aspect ratio designed specifically to reduce inertia and air damping effects on massive, oversized pocket watch dials. Form always follows function. We know what the hands look like, but how do they hold on? Let's examine arbor fixation, the physics of the cannon. We are managing intense friction fit against violent kinetic inertia. Look at the 3 structural cross-sections on the screen. The structural interface between the thin hand and the steel movement arbor dictates absolute rotational stability. Remember, a hand is a microlever. During a sharp shock, kinetic inertia aggressively attempts to overcome the friction fit and spin the hand off its mark. Type 1 is flat without cannon. A simple hole is punched directly in the flat hand body. The physics here dictate the lowest possible profile, but it provides minimal vertical friction surface area. It is highly vulnerable to shifting under shock. It is generally avoided in high-end watchmaking. Type 2 is the stamped cannon, or cannon embouti. An integral cylindrical collar is drawn and stamped directly out of the hand's own base material. It provides a raised vertical wall, massively increasing the friction grip surface area. It offers an excellent balance of manufacturing cost and kinetic security. This is the modern industry standard. Type 3 is the fitted cannon, or cannon report. A separate, precisely machined cannon, often made from a harder metal like beryllium copper, is riveted or laser welded into the softer hand material. It provides ultimate grip security and allows for the precise, microscopic adjustment of the pressing force. This architecture is absolutely mandatory for heavy, oversized hands and high-G chronograph zero reset applications where the violent snapback forces would instantly strip a standard stamped cannon. What are these hands actually made of? Let's review the metallurgy and optics of hands. We are constantly balancing specific density against aesthetic longevity. Look at the materials matrix on the screen. Material selection for hands is a relentless battle against kinetic inertia. Lighter hands drain less torque from the mainspring and violently resist shifting during physical shock. Let's look at the base materials. Brass, Liton, is the industry standard. It is soft, extremely easy to stamp and form, and takes electroplating beautifully. It has a moderate density but absolutely requires protective coating to prevent rapid oxidation. Steel, Acier, possesses significantly higher tensile strength. It is absolutely mandatory if you want thermally glued hands, and is heavily utilized in high-stress sport watches. Gold, or, is highly dense. Because of its weight, it increases inertia, but it is exclusively used in precious metal watches because it retains its natural luster forever without requiring any anti-corrosive coatings. Aluminum is ultra-lightweight. It is selected specifically to drastically reduce inertia on massively oversized dials, and is colored easily via chemical anodization. Look at the surface treatments on the right. We use electroplating for standard colors. But look at thermal bluing. Watchmakers meticulously flame heat raw steel to exactly the right temperature to create a resilient, deep blue oxidation layer that acts as profound rust protection. And finally, luminescence. We structurally infill the frames with superluminova. But read the warning: crystalline structure fracture risk. If the metal frame bends even slightly, the rigid luminous lacquer will shatter and fall into the movement. Frame integrity is paramount. We step back from the dial and return to the massive armor of the case itself. Welcome to Habillage Metallurgy, Engineering Constraints. We are defending the caliber against the environmental battlefield. Look at the material hierarchy pyramid on the screen. Read the environmental battlefield criteria on the left. The watch case sits directly on the skin, enduring constant exposure to the most aggressive chemical and physical environments. 1. Chemical inertness. The metal must perfectly resist oxidation and degradation from acidic lactic sweat, salt, cosmetics, perfumes, and atmospheric pollutants. 2. A mechanical resilience. It must resist severe abrasion and catastrophic impact deformation over decades of use without failure. 3. Aesthetic longevity. It must maintain its microscopic finish, its polish, and its architectural beauty without yellowing, peeling, or tarnishing. Look at how the industry solves this via the material hierarchy pyramid on the right. At the base, we have electroplated brass. Historically common, but today strictly restricted to budget and fashion tiers because the plating inevitably wears off, exposing the corrosive brass to the skin. At the core, we have stainless steel. This is the absolute standard for mid to high range and professional tool watches. It balances extreme durability with reasonable manufacturing costs. At the premium level, we have precious metals, gold, platinum, and silver. These are the traditional pillars of luxury, chosen for their intrinsic value and chemical immunity, despite their physical softness. And at the apex, we have high-tech synthetics and ceramics, titanium, zirconium dioxide, and carbon composites. This is the bleeding edge of extreme durability, offering virtually scratch-proof and entirely hypoallergenic armor. Let's examine these tiers in detail. Let us examine the traditional pillar of luxury, precious metals, and the hallmarking framework. This sector is governed not just by physics, but by strict legal verification. Look at the metallurgical and legal visuals on the screen. Precious metals are utilized for their permanent resistance to oxidation and unparalleled aesthetic luster. However, pure 24K gold is much too soft for habillage, it would deform instantly. Therefore, it must be alloyed. Look at the standard alloys. Pure gold is alloyed with copper, silver, or palladium to radically increase its hardness and alter its color to yellow, rose, or white gold. The absolute standard for Swiss watchmaking is the 750 standard. This means 18-karat gold, which mathematically equals a minimum of 75% pure gold by mass, 750 parts per thousand. Platinum is typically used at a highly dense 950 purity. Silver is prone to sulfuration, tarnishing, but is standard at 925 sterling. Now, read the Swiss hallmarking law in the bottom box. This is a severe legal constraint. By law, any watch case claiming to be a precious metal must feature official assay office hallmarks, or poinçons, permanently stamped into the metal. It must bear 3 marks. 1. The manufacturer's mark, identifying who made the case. 2. The purity mark, mathematically verifying the exact fineness, e.g., the 750 scale symbol. 3. The state guarantee mark. Since 1995, all Swiss precious metal watch cases must bear the head of a St. Bernard dog. If that dog is missing, the watch is legally not Swiss gold. Moving down the pyramid, we encounter the workhorses of the industry. Let's review core metals, stainless steel and brass. We will examine the intense machining challenges, electroplating, and MIM technology. Look at the 2 material profiles on the screen. On the left, stainless steel, e.g., 316L, 904L. This is the ideal material for durable, professional watch cases, offering exceptional hardness and wear resistance. However, read the challenge. It is exceedingly difficult to machine. Traditional methods like stamping, turning, and milling rapidly wear down expensive carbide cutting tools, making complex, multifaceted case geometries massively expensive to produce. The innovation solving this is MIM, metal injection molding. Stainless steel powder is mixed with a polymer binder and injected as a liquid into complex molds, allowing incredibly intricate case shapes to be produced at high volume and much lower cost before sintering. On the right, we have brass, or les latins. It is a soft alloy of copper and zinc. It is exceptionally easy to machine, making it highly cost-effective for case blanks. But read the vulnerability. Raw brass rapidly corrodes and turns green if exposed to acidic human skin. It absolutely requires multi-layer galvanic protection. Look at the electroplating strata diagram at the bottom. You cannot just plate gold over brass. You start with the base brass, apply a thick copper plating undercoat to seal it, add a precious metal barrier undercoat like palladium or nickel to prevent atomic migration, and only then do you flash the final finish of gold or rhodium. If any layer fails, the case rots. We finally reach the absolute apex of the material pyramid. Welcome to the technical specs of black zirconia, 3YTZP. This represents the bleeding edge of scratch resistance and advanced synthetics. Look at the quantitative data on the screen. What is a ceramic? Ceramics are inorganic, non-metallic, crystalline compounds, in our case, zirconium dioxide, ZrO2. They are engineered to offer unparalleled scratch resistance and are completely hypoallergenic, containing zero nickel or cobalt. Let's look at the quantitative specifications. First, hardness. It registers a staggering 12 gigapascals, or roughly 1200 on the Vickers scale. Remember, standard stainless steel sits around 200 to 600 HV. Zirconia is virtually immune to daily scratching. Second, density. At 6,000 kilograms per cubic meter, it is heavier than titanium but notably lighter than steel, providing a highly comfortable, balanced wrist presence. Third, and most crucially, flexural strength. It registers between 800 and 1,000 megapascals. This is exceptionally high for a ceramic. Historical ceramics were incredibly brittle and shattered if dropped. Modern yttria-stabilized zirconia flexes microscopically to absorb shock, preventing easy shattering. Fourth, chemical inertness. It is 100% immune to oxidation, it laughs at UV degradation, and it is totally impervious to acidic corrosion from sweat or salt water. It will look exactly the same in 500 years as it does today. If ceramic is so hard that it destroys standard cutting tools, how do we actually shape a watch case out of it? Let's review high-tech ceramics, manufacturing and shrinkage physics. We are looking at CIM injection molding and the terrifying reality of 30% volumetric reduction. Look at the three-step diagram on the screen. Step 1 is CIM, or ceramic injection molding. We do not cut a block of ceramic. We take raw, microscopic ceramic powder, mix it with a polymer plastic binder, and melt it. An extruder injects the slurry into a complex steel mold to form an oversized, fragile green body case. Step 2 is debinding and sintering. The fragile green body is placed in an industrial furnace. Slowly, the polymer binder is burned out entirely. Then, the furnace is ramped up to extreme temperatures around 1450 degrees Celsius. At this heat, the raw ceramic powder particles literally fuse and weld together at the atomic level, creating the final, ultra-dense crystalline structure. But look at step 3, the shrinkage factor. This is an engineering masterclass. As the binder burns away and the particles fuse, the parts shrink volumetrically by a massive 20 to 30% during baking. Look at the diagram comparing the oversized green body to the finalized case profile. The engineering nightmare is this: the tooling molds must be mathematically oversized with absolute perfection so that the violently shrunken, fired case perfectly fits standard, zero-tolerance O-rings and rigid sapphire crystals. If the math is off by 1%, the case is scrap. We have built the case, now we must attach it to the human. Let's look at securing the caliber, bracelet and strap architectures. This is about mechanical reliability, aesthetics, and legal integration. Look at the two primary types on the screen. The core purpose is absolute. The strap or bracelet must secure the heavy, expensive watch case to a rapidly moving wrist with absolute mechanical reliability, while simultaneously providing a vital aesthetic continuation of the case architecture. Type 1 on the left is the integrated strap, or Le bracelet Saut à la boîte. Architecturally, it is an organic, physical continuation of the case. It is either permanently welded or heavily machined as one contiguous solid metal unit. But read the legal constraint warning in yellow. Under Swiss law, if the case is constructed of a precious metal, the integrated bracelet must possess the exact same millesimal fineness, tighter. It cannot legally vary. You absolutely cannot attach a cheaper 14K integrated bracelet to an 18K case. The law views an integrated architecture as a single, unified object. Type 2 on the right is the removable strap, or Le bracelet immovable. Architecturally, it is connected to independent case lugs, corns, via engineered spring bars. This allows infinite material swapping between leather, rubber, and steel. Look at the dimensioning rule. The strap width must be manufactured to exactly match the internal lug width, the l'entrecorns gap. If the strap is too narrow, it will slide laterally along the pin, eventually catching the collar of the spring bar, compressing it, and causing total catastrophic failure. The entire survival of a $100,000 watch relies entirely on two microscopic metal tubes. Let's examine mechanical linkages, lugs and spring bars. Look at the highly detailed engineering schematics on the screen. Let's look at lug hole configurations on the left. First, blind holes, or trous-bornes. The inner holes do not pierce the smooth outer lug surface. To remove the strap, you must approach from underneath with a specialized fork tool. This is the absolute standard for modern dress and luxury models to maintain a clean aesthetic. Second, through holes, trous traversants. The hole passes entirely through the steel lug. This allows for rapid, secure removal simply by pushing a pin directly from the outside. It is heavily favored on vintage designs and dedicated, rugged tool watches. Now, look at the spring bar variants, barrettes à ressort, on the right. We have the standard pivot. A spring-loaded tip enters the lug hole. Simple and effective. We have the security collar, de sécurité. This is vital. It features a flanged collar specifically designed to be gripped firmly with a forked tool, preventing your steel tool from violently slipping and deeply scratching the precious metal lug during a strap change. We have the hole-in type. These female ends are utilized when the case lugs themselves feature solid, protruding male pivots. Read the assembly warning box at the bottom. Physical verification of pivot seating is absolutely mandatory. If you install a strap and fail to ensure these tiny steel cylinders have fully snapped into their locking holes, the result is a catastrophic drop of the watch directly to the concrete floor. We have reached the summit. Please look at the Chapter 12, L'Habillage de la Montre Master Synthesis map on the screen. This matrix represents the complete structural integration of all external watchmaking components we have studied. Let's trace the quadrants. Top left, constraints and health. We established the intense environmental crucible. We must navigate chemical risks, tritium radiation limits, and crushing hydrostatic pressure. We must engineer survival against 8,000 G shocks, 70-degree thermal swings, and high-intensity magnetic fields. Bottom left, displays and interface. We evaluated the cognitive superiority of analog hands versus the mechanical density of alphanumeric discs. We engineered the brass dial plate, explored the intricate typography, and broke down the kinematic physics, proportions, and typologies of the microlever hands. Top right, case engineering and seals. We built the chassis. We compared elastic one-piece shells to professional three-piece modular armor. We established the absolute law of stem coaxiality. We then sealed the fortress, utilizing dynamic O-rings, flat gaskets, anaerobic adhesives, and extreme pressure screw-lock crowns to protect the fragile engine inside. Bottom right, materials and straps. We balanced density, hardness, and aesthetics. We analyzed 18K precious metals and their strict hallmarks, the injection molding of stainless steel, and the bleeding-edge shrinkage physics of 12 GPa zirconia ceramics. Finally, we safely chained the entire machine to the wrist using precision lug and spring bar architectures. As we conclude this massive chapter, I leave you with the final review: Habillage diagnostics. Look at the breathtaking macro photograph of the finished timepiece on the right. Before a watch ever leaves a professional manufacturer, it must pass the final assembly verification checklist on the left. Ask yourselves these questions. 1. Allergen and legal compliance. Does the case material comply with EU REACH nickel release laws, and does it carry the required Swiss St. Bernard hallmarks? 2. Sealing integrity. Are absolutely all penetration points, the crown tube, the pushers, the crystals, the caseback secured with properly lubricated, unpinched elastomeric gaskets? 3. Kinematic clearances. Do the sweeping hands perfectly clear each other, the dial surface, and the underside of the sapphire crystal during a full 360-degree rotation? Are the dial feet firmly clamped against shock? For attachment security, are the correct, width-matched spring bars utilized, and are they audibly and physically locked into the case lugs? Read the course conclusion. Habillage is the engineering of boundaries. It meticulously negotiates the hostile, unpredictable external environment to protect the fragile, perfectly ordered micromechanics within, while simultaneously providing the sole aesthetic and functional interface for the human user. It is where raw physics meets high art. Module complete. In our next session, we will finally combine the movement and the habillage as we enter Chapter 13, Complications and Advanced Chronometry. Thank you for your intense focus. Class dismissed.